Hi, I'm John McLoon. I lead the technical services team for Wolfram Research in Europe, where we do computation and data science projects for customers using Wolfram technology. And Wolfram is the company behind the online knowledge engine Wolfram Alpha, the mathematical computation system, and the computational programming language, the Wolfram language. I'm also the co-founder of computerbasedmath.org, which is an organization trying to rethink the maths educational curriculum in a way that actually assumes computers exist. Now, what I wanted to do today was to talk a little bit about the way that Wolfram Alpha has approached question answering on the web compared to ChatGPT and other large language models. And this is really a contrast between the fundamentals of statistical AI versus symbolic AI. So if we start with the exciting new large language models that have appeared very recently and are still emerging as we speak, they are simply statistical models to predict what word comes next after previous words. What's exciting about them is that they are sufficiently rich in that statistical structures that they've built that the next word that follows and the next multiple words that follow can be very human-like in their ability to answer a question. The text that follows a question is the answer, or the explanation behind a statement, or generative content like writing poetry. LLMs and other statistical AIs are very good at some things, but they also have weaknesses. Let's talk a little bit for a moment about what they're good at and then what they're not so good at. They're very good at handling a wide range of inputs. We as humans are very good at language, and we've got years of experience in phrasing things in different ways and understanding different ways of putting them. And up until now, that's been quite a challenge. So if I give some kind of complicated way of asking a question, ChatGPT and its competitors are very good at turning that into simple, pithy questions. The kind of things that Wolfram Alpha would struggle on can be rephrased very simply by LLMs. They're also very good at handling poorly defined or poorly understood fields. So here I've asked it, how should I train a dog to sing? I'm sure there's no solid theory for how you train a dog to sing, but it's come up with a very plausible explanation of how one might go about it. And of course, the thing that's getting everyone excited about them is they give the appearance of really human-like interaction to the point that they could fool you into thinking they're really understanding things. So that's things like creative writing, like writing a poem or a song, or writing in a particular style, or rewriting text and summarizing it, or extrapolating on text. These kinds of things they are achieving in ways that have never been possible before. But large language models are not good at everything. Because what they do is probabilistic, and there's no real understanding behind what they're coming up with, they tend to fall down where things actually require proper understanding to achieve. So they're not very good at things like logic and rational and computational thinking. So, for example, if I ask this question of Alice is older than Bob, Bob is older than Charlie, Charlie's younger than Derek, and ask the question, is Alice older than Derek? That's not a very complicated piece of logic. And while it's come up with a nice explanation here of why it concludes that Alice is indeed older than Derek, the conclusion is wrong. And it doesn't take too much thinking about to realize that there isn't enough information to decide the answer to that. They're also generally very bad at following rules. So even something as simple as a piece of arithmetic, here I've asked it to add two numbers together, which is in ChatGPT 3. The answer is plausible, and in fact, it is correct for the first three significant digits. But if you compare it against the actual computation here that I've done in the Wolfram language, it's actually wrong. Most of the digits are just fiction. And as soon as you go to something more complicated, like here's some calculus asking for the integral of some formula, even though the narrative is very convincing about how it's gone about it, the answer is just wrong. When things start to require processes and steps that need to be precisely followed, this kind of approximate random way of assembling the words really just falls down. Also, by design, they are not intended for large amounts of information. The working memory of GPT-3 is about 2,000 tokens, so a page, I guess, of text. GPT-4 has pushed that back quite a long way to 20,000 odd tokens, but that's still, a few pages or a small chapter of a book. That's the entire working memory. Now, if you're doing anything in data science, that's a trivial amount of data. I routinely do projects with hundreds of millions of numbers, and data science, statistics, and maths are very geared towards that kind of large data processing, but large language models just really don't even attempt to take that on. But the thing that most people have been concerned about is, in the end, reliability, that they have a tendency to hallucinate and just make things up. So here's a question I've asked of GPT-3. I said, provide some data on livestock populations in the country of Turkey. And it's come up with a perfectly sensible looking essay. And I was particularly drawn to this point here where it says, based on data from Turkstat. On this occasion, Turkstat is a genuine thing. GPT has been known to completely fake references to support its argument. In this case, this reference is a real thing. But it turns out it is not a supporting reference. If you go to Turkstat and drill down through the pages of information and eventually find the document that answers this question, you see that the sheep population is 42 million, not the 33 million that this article claimed. In fact, all of these numbers are wrong. They're all in the right ballpark, so they're plausible, and large language models are very good at plausible. But this idea that it can be trusted because it's cited is just, both these things are, there's no reliability going on here at all. Okay, let's go now to what we've been doing with sort of symbolic AI and the way that Wolfram Alpha and Wolfram technology works. Our word for this symbolic AI is computation. And computation is really where you have defined rules of behavior for structured inputs. So if you take the example of adding those two numbers together, those are structured inputs, integers. We know what those things are, and we know the rules of behavior of adding, subtracting, multiplying, doing all of these things to integers, very rule-based. It turns out computation is a really broad area that we've been spending the last 30 years trying to integrate computation from mathematics like theorem proving and graph and network analysis and calculus and statistics with things that you might see more of in physics like differential equation solving or image processing, or engineering calculations like control theory, chemistry calculations like energy bond calculations or spectroscopy, and all kinds of other areas like geo and data computations. Machine learning falls into that as well. Business things like time series and financial calculations, and even in things like digital humanities. Now, what you see on the web with Wolfram Alpha looks a little bit like GPT, in that you type in a question and you get an answer. But actually what we're doing is applying a very rule-based grammar setup to the question that you ask and turning that into a structured piece of information like an integer or like an entity that represents a thing in the world, like a city or a person. And then we're applying computational algorithms to that, fed by live and stored data in order to generate the answer. Most of this is highly deterministic algorithmic processing under the guise of conversational AI. So what is that good at and not good at? Well, it turns out that it's almost the complete opposite of the statistical large language model strengths and weaknesses. The computation is extremely good at logical, rational thinking. So my who was tall a question, we can code up symbolically as this quantifier elimination type question and ask the question, is it true that for all possible setups there, Alice is always tall and Derek? And it says no, it can conclude that that isn't true. It can follow rules. So here's the same calculus question that I asked before, and in the Wolfram Alpha world, we get that absolutely correct, better than any human could do. We also, of course, computation is very good at handling large amounts of information, and it's also very good at deterministic and reproducible and understandable rules of behavior. So the reliability is very high. If it can do something, it'll do it every time. Of course, our approach isn't good at everything. So the very things that the large language models are good at, that's where we tend to be quite weak. We have natural language input, but anyone who uses Wolfram Alpha knows that you kind of have to get the hang of the way to pose a question, because if you're a little bit too flamboyant in the way that or exotic in the way that you phrase sentences, or you make sentences too complicated, it very quickly can't handle that level of complexity. It's also not at all good at poorly defined or understood fields. If there aren't rules of behavior, then it can't deal with that. So writing poetry is difficult because it's very hard to actually write down what the rules of a good poem are. They're just one of those things you know when you hear it. And that kind of human-like you know it when you see it is not a good basis for rule-based computation. And they're not very good at looking human-like. It's not a case of trying to make the picture one is better than the other. They both have their own strengths. Our vision at the moment, and we're putting a lot of effort into, is to try and bring the two worlds together. Can we take the best of the large language models and other statistical generative AIs and put it together with the strengths of computation? And here's a few different ways that emerges, and we're building out the tool set very rapidly right now to make this something that will be easy for you to be able to do yourself. So here I have the idea of computation-driven narrative. In this case, computation is very trivial here. I'm using financial data from databases that I'm using the Wolfram language to structure into open, high, low, close values, and then I'm feeding that as the basis of a stock trading website's narrative of today's action. Now, because this is not based on the big compressed corpus of knowledge that is static and out of date from a year ago when the large language model was trained, the facts are based on computation that I've just computed, then this narrative becomes much more reliable. And large language models tend not to hallucinate when they're fed the facts as part of the inputs. They tend to use them very reliably. Another key thing that we're doing is the same kind of idea, but reversing the lead. And we were invited to be one of the first plugins for ChatGPT that were launched a couple of weeks ago, where if you enable the plugin, and you have to be at the moment on the invitee list from OpenAI to get access to the plugins, but you check out the Wolfram plugin. Now, when I asked this question that it lied to me about before, what are the populations of different livestock in Turkey, you see this used Wolfram button appears. That is the large language model figuring out that this is something that we might know the answer to. It's called Wolfram Alpha, asked for the facts, got the facts back, and has now written, in this case, a much more terse narrative, but based on those correct facts that it requested. And because of the generality of the large language model, it's very good at spotting the kinds of things where the Wolfram Alpha might be able to inject some useful information. And you can always prompt it by saying, ask Wolfram what are the populations of different livestock in Turkey. And because we can compute visually as well, then adding a follow-on prompt here, make a bar chart, the large language model took the data that it had in its narrative, pulled those numbers out, and sent them to Wolfram Alpha and said, can you make a bar chart of these values? And then it's injected it back into its answer. So if we want to join together these two different worlds, one of the questions is, how do we go about that? And it turns out there's a choice that's kind of interesting. If we look behind the scenes at what happened, if I expand the use Wolfram button in our previous query, you'll see that Wolfram Alpha's ability to take more basic but still natural language inputs is the way they've chosen to communicate. So they're using English as the interchange language between the two different AIs. And this is how it retrieved the values, and it got them back in a sort of list of values, but not especially structured. But when I then went on and asked for the bar chart, here it actually wrote Wolfram language code, and the code itself was evaluated. Now, a lot's been made out of the excitement of the way large language models can write code, but because code writing is ultimately one of these rule-based worlds, actually there's a limit before they break down, even though there are some very impressive examples in isolation. Sooner or later something goes wrong. But there's two things that we have here that are advantageous. One thing is that because the Wolfram language is very high level and designed to be very human readable, actually it takes less code, typically 10 to 20 times less than Python or Java, to express the same ideas, and they are higher level, more language-like ideas and less code-like, which actually makes it easier for the large language models to generate. And on top of that, we've been building feedback mechanisms that allow hints to be given back to the large language model when the code doesn't execute, to explain what the errors are and ask the large language model to try again. And you actually get sort of a loop of conversation going on where the LLM writes code, Wolfram language says, well, I don't recognize that command, that's not a valid command. The large language model corrects itself, and eventually you get into something that can be executed. And these can be reasonably high-level expressions of idea. Here I've tried to describe the collapse conjecture in words, and it's written a quite significant snippet of code here to generate this plot of the waterfall sequence or collapse sequence. And finally, another big win for the integration is the handling of unstructured data. So anyone who does data science knows that getting the data straight usually is the majority of the work. And it turns out that's the bit, when it comes to data science, that large language models are quite good at. So one of the things that you can do is you can use its ability to do what's called few-shot or one-shot learning to give it examples of how you want to restructure. And large language models are very good at that. So from a code level, I can embed the capabilities of the large language model in order to make import filters very easily. So in this example, I've given a description of what I want to achieve. We're going to get the name, height, and age of some people. And I'm going to give it some examples of this is the input, and this is how I want to represent it. So I want a Wolfram language structure, and I want Wolfram language notions of quantities, and Wolfram language notions of symbolic missing data. And then having set that filter up, I can now apply it to some unseen data. And what we get back is now a computable data set where all of this has been turned into the Wolfram language structure that allowed me to tabulate this very easily. And these quantities are now proper entities within the Wolfram language, so I can do computations on them, like let's get the first person's age and convert it into days. Leveraging the built-in knowledge that large language models have about short-range structure makes this kind of restructuring of data much, much more efficient than rule-based approaches that one would have had to build up before. So we've got these two worlds, the statistical on the left, the computational on the right, and in the end, we're trying to build all of the links in all the different directions of when one can call the other to help out on the things it's not good at, in order to have the same kind of start point, natural language input or unstructured data input, and insight output, but using the best of both worlds. Well, I hope that's been an interesting viewpoint, and if you need more information, follow the links here or feel free to write to me at my personal email address. Thank you.